This is Keeper 3.4, curve sketching f to f prime. So we will be starting with the function and we will be sketching the first derivative and sometimes the second derivative. Okay, the relationship between f prime, and f double prime. You need to cut this out and glue this into your Keeper or write it very neatly. This is very, very important. You have to memorize these relationships and be able to use them. So the first column, you're looking at what's happening in the original function f. If you are given a cusp, corner, discontinuity, vertical tangent, these are all places where your function cannot be derived. You do not have a derivative at that cusp, corner, discontinuity, or vertical tangent. So the first and second derivative would not exist. I'm going to try to sketch like an example. A cusp would look like something like that. A corner, think of absolute value, or maybe I'm going like, oh, this isn't very good, linear, and then like horizontal. That's a corner. It's a sharp corner. It's not curved. It's a point where you can't find, like that minimum doesn't have a derivative of 0 because it's got a negative slope and a positive slope. Is not flat anywhere. You know what these discontinuities look like? A vertical tangent is where in the middle of your curve you have a section that's completely vertical and you know that the slope doesn't exist at a vertical line. So maybe something like that. And so there's your vertical tangent. Okay, so if you have any of these places in your function, then it doesn't exist in the graph of the first derivative, and it doesn't exist there at the graph of the second derivative. Okay, local max or local min, max and min are called extrema. That will give you a derivative of 0. And so that's where it's going to be on the x-axis. So if you have a point where your graph is increasing and then decreasing, you have a local max. And so wherever that x value is, so increasing and then decreasing, so at this x value, the derivative would be 0. And so 0 will be on the x-axis for the first derivative. It's an x-intercept. Same is true for a horizontal tangent, which is like kind of what this picture looks like here because I drew it a little flatter than I meant to, but any place where it's horizontal, that's a slope of 0. And so that will be on the x-axis in the first derivative. Okay, then we're going to look at sections of the graph where it's increasing and decreasing. So wherever the function is increasing, that's going to be positive y value in the first derivative. So that means you'll sketch it above the x-axis. So this is like an increase. Wherever your graph is decreasing, so like that, then the derivative, think of that, that would have a negative slope. So it's negative in the y values, so below the x-axis in the sketch of the first derivative. Okay, when we talk about concavity, concavity is giving us information for our second derivative. We're going to first look at the concavity, and then you're going to see what it does to the first derivative and the second derivative. So if your graph is concave up, so a parabola opening up, that means that the first derivative is going to be increasing, and the second derivative, if the first is increasing, then the second derivative, you take the derivative again, it's going to be positive above the x-axis. And then concave down, if you have a concave down section in your function, the first derivative will be decreasing. So like that. something like that, decreasing. And then if you're sketching the second derivative, it will be below the x-axis. Points of inflection are where your graph is changing concavity. So you're changing from concave up to concave down, or concave down to concave up. So say you have something like this. So this first left half that I drew, that would be concave down, and then it's switching to concave up. So this right here is a point of inflection. That's going to tell you that the first derivative's sketch will have a local extrema there, either a max or a min. And then the second derivative is going to be changing signs. So it's going from above to below the x-axis, or below the x-axis to above the x-axis. So keep looking over this. You need to understand it and be able to use it. This next section is going to have 4 different sketches, but all with the same directions. So to save some time and space in your keeper, write these directions down once. What can we say about g, g prime, g double prime for each segment of the graph y equals g of x? G is talking about this function that you're looking at. G prime is talking about what will be happening on the graph of the first derivative, and G double prime is talking about what is happening on the sketch of the second derivative of this graph. So first we want to say what's happening right here on G. And if you trace from left to right on this graph, you notice that it's increasing. And this is also concave up. So I always think of concave up as like a cup. And so this looks like part of a cup. So we're going to write that down. G is increasing and concave up. Now, based on knowing that G is increasing, we can say that its first derivative will be positive. And knowing that it's concave up, its first derivative will also be increasing. So if you were sketching this first derivative, positive would mean that we're sketching it above the x-axis, positive y values. And when you're sketching it above the x-axis, it's going to be increasing from left to right. If you're sketching the second derivative, then you see that the original is concave up, meaning that the first derivative should be increasing, or is increasing. So since the first derivative is increasing, the second derivative is positive, meaning above the x-axis, positive y values. Okay, so you already have these directions written down, so now you just need to draw this sketch. And if we look at function g, this sketch that's given to us, and you trace it from left to right, you see that it's decreasing. And this is also concave up. It's like the other side of the cup. If you put the last piece over on the right side of this, then you could see that it's shaped like a cup. So this is concave up. So G is decreasing and concave up. So now let's talk about what's going to happen on the first derivative of this part of the graph. Because G is decreasing, we know that the first derivative will be negative, meaning below the x-axis. And because G is concave up, the first derivative is increasing. So if you're sketching this segment and you're sketching the first derivative, you're going to draw a section that's below the x-axis that's increasing from left to right. If you were asked to sketch the second derivative, the first derivative was concave up. No, I'm sorry, the original was concave up, meaning the first derivative is increasing, and so the second derivative is going to be positive, or above the x-axis. Our third sketch, So we look at what is happening at G. G is decreasing from left to right, and this is part of a concavity that's concave down. I always think about the concave down. Two sections, if you put them together, it looks like a frown, down, frown. So G is decreasing and concave down. Since G is decreasing, the first derivative will be negative. And since G is concave down, this negative section, which is like below the x-axis, will be decreasing. And then the second derivative of G is going to be negative, or below the x-axis. So the concave down in the original function meant that the first derivative is decreasing, and so the second derivative is negative. And our final sketch, if you look at it, you see that G is increasing from left to right, but it's still concave down. It's part of a frown, like the left side of your frown. And the first derivative, since G is increasing, the first derivative is going to be positive. And because of the concavity of the original being down, it's going to be decreasing. So the first derivative is positive above the x-axis and decreasing from left to right. And then the second derivative, if you go back and you look at concave down, which means decreasing, it tells you that the second derivative is negative. So it would be sketched below the x-axis. For the rest of your notes, you should have these graphs printed where you can glue them in. There are 5 of them that we're going to be going over. So this is the first one. This is the function of, we'll call it f of x. It's an original function, and we want to graph the first derivative. So you're going to think about that first slide that you cut, and the first thing that you put in the keeper, the relationship between f and f prime, the first derivative. So you're going to look at this graph, and you're going to see, where is this graph increasing? Where is it decreasing? Where does it have a maximum or minimum? And we're going to draw this f prime line. You can call it a sine line or f prime line, and we're going to put positives to represent that it's increasing, and we're going to put negatives to represent where the graph is decreasing. And we're going to use this information that we put on our sine line to help us sketch our graph of the first derivative. So if I trace my original graph from left to right, it's decreasing. It's decreasing everywhere. There's nowhere that it turns and starts to increase. So I would put negatives all across this sine line. But since it's a linear function, it's decreasing at a constant rate. So since we know that the rate in which it's decreasing, which is its slope, I'm not just going to put negatives. I'm going to put negative whatever the slope is. So if I look at 2 points on this graph, I'm going down 1 and then over 2. So this function has a slope of negative 1/2. So instead of putting all negatives across my sine line, I'm putting all negative 1/2 because I can be more specific since it's linear. Now I need to sketch the derivative based on what's on the sine line. So if I just had negatives, then I know that that would mean negative y values, that I'm sketching below the x-axis. But since it was a constant rate of change and the slope is negative 1/2, the first derivative is all at y equals negative 1/2. So that's the sketch of the first derivative. Here's your second graph. So we're going to do the same process every time where we draw our f prime line. We're going to draw it down below. we're going to go back and we're going to look at this graph to see where is it increasing, where is it decreasing, where does it have a maximum or minimum. And we're also going to look for any of those other issues like a cusp or a corner or a hole or any discontinuities, vertical tangent also, to put on our sign line. So if I trace this graph from left to right, I start here and I'm tracing and I'm increasing all the way until I get to x is -1. And -1 is a maximum because then it's changing to decreasing. So you see, like now it's decreasing there. So -1 is a point that I want to put on my sign line because it's where my graph is changing from increasing to decreasing. And at that maximum point of -1, your slope would be 0. So there's my -1. The reason it has a slope of 0 is everywhere where it's increasing in yellow, if I had to draw a tangent line, they would all be lines with a positive slope. Where I have the blue, if I had to draw a tangent line to any point on this side, they'd all have a line, so negative slope. If I had to draw a line at this maximum right here, a tangent line, whoops, that is not horizontal. Let me just go ahead and erase that. But you get the idea. It would be a horizontal line at y equals 0. So that's why the 0 is there. On the left side of -1, where x is less than -1, I have all positive, representing it was increasing during this interval. And then negatives where x is greater than -1 because that's where it's decreasing. Again, picture drawing a line tangent to any point over there and you'd see positive slope where x is less than -1 and a negative slope where x is greater than -1. Take this information and sketch the graph of the first derivative. So where x is, or where I have x is less than -1, where I have all these pluses, positive means it needs to be drawn above the x-axis. 0 is on the x-axis and negative is below the x-axis. So I'm starting with the 0. It's on the x-axis. Positive is positive y values, so it's above. And negative is negative y value, so it's below. And this is a quadratic function, and you'll see in a later chapter why it turns out to be linear. But that's the answer for your first derivative. Here's our third example. This is a graph of absolute value function. When we talked about absolute value, we talked about how you could separate it. It's a piecewise function. So you have the absolute value of x is really positive x and negative x over just different intervals. So got my sign line, and I can see that my graph is decreasing and then increasing. And it's changing at 0. And at 0, right here, this is a corner. And so 0 is an important point on our graph, is where it's changing from increasing to decreasing. And the other one, it was a nice curve. So it had a horizontal tangent, and horizontal lines are 0. But here, this is a corner, so this is a place where my graph is not going to exist. It does not exist. If I look on the left side of 0, where x is less than 0, and I trace, I'm going down here. This is decreasing. So that's going to be all negatives. And then I'm increasing. So on the right side of my sign line, I'm going to have all positives. So I didn't just put negative, and that's because this is a linear function. So I can see that it has a slope of -1. On the right side, it has a slope of +1. So anytime you can find the actual slope, because it's linear, you're going to use that. If it's a curve, you would just say it's decreasing or it's increasing. But if it's increasing or decreasing at a constant rate, you're going to put what that slope is, and we're going to use it. So when you sketch this first derivative, the left side is y equals -1. It has an open point because it doesn't exist at 0. And then where x is greater than 0, then y equals 1. And that's also open. So I had to make sure to put an open point there because it does not exist. The first derivative doesn't exist at a corner. Okay, this is your next example. And go ahead and every time draw your f prime line or sign line underneath. And when I look at this graph, I see that it's increasing everywhere. And so on my sign line, I'm going to just put pluses everywhere. And it's not a constant rate of change. It's not a constant increase since it's not linear. So I can't put a value because it's changing. And I'll just have the positives. But one thing you have to pay attention to this curve is as x is approaching -infinity. So right over here is getting closer and closer to 0. So there's basically a horizontal asymptote here. And since it's getting closer and closer to 0, you're getting closer to approaching a horizontal line, and a horizontal line has a slope of 0. So that's important when you see that your graph is approaching that y value of 0. You're going to need that to happen in the first derivative also. So on my sign line, first I'm going to notice, or I'm going to note on the left, that it should be close to 0 because that's getting close to being a horizontal line. And a horizontal line has a slope of 0. And then when I trace from left to right, like we already talked about, it's increasing everywhere, so I'm going to put pluses everywhere. So the pluses, the positives, mean that you're going to have positive y values. So this whole graph is going to be above the x-axis. Basically, it's going to look like this original graph because we need this left side to be close to 0, and it's a curve that's increasing and above the x-axis. So your sketch is going to look very similar. Even if it's right on top of it, then it's fine. Just make sure it's continuing to increase and it's above the x-axis and it's not linear, and you need that left side close to 0.